Okay. Hi, everyone. My name is Guillaume. I'm a PhD student at EPFL working on the .t compiler, and today I'd like to talk to you about this cool new format we call TASTY and what it means for the future of Scala. So to begin with, I'd like to talk about upgrading Scala. So imagine you're writing this really cool app in Scala, and it's using Scala 2.12. But Scala 2.14 was just released a few days ago. It has all these cool new things like the new collections, and you really want to use it. So you say, OK, I'm just going to change the Scala version in my program from 2.12 to 2.14. And if you just use the Scala standard library, then that's fine. But as soon as you have dependencies which have been already compiled against 2.12, you can't do that. Because these dependencies won't be able to use the new standard library and the new version of Scala. And these dependencies themselves might not be able to upgrade to Scala 2.13 until their own dependencies have been upgraded to Scala 2.13. And whoa, screen is a little bit off. Okay, let's see. Can I? Yeah. Oof. Let's see how that goes. So what needs to happen is first all the dependencies at the root of the tree, which usually are things like Scala test, Scala check, cats, need to upgrade to 2.13. Then the libraries that uses these libraries that you depend on need to upgrade. And then finally, you can start using Scala 2.13. So why does this happen? What's going on here exactly? So to explain that, first I need to explain what binary compatibility is. So in a very big nutshell, imagine I have a project A, which is compiled against some specific version X of project B. And then I want to run this project with a different version of project B. And if it doesn't work, where it doesn't work usually means like crash at runtime, then we say that X and Y are binary incompatible. And if you want more details, you should go see this awesome talk, which is on YouTube by Sebastian, about how to design libraries for source and binary compatibility. Okay, so we understand this, but why does Scala need to break binary compatibility every 2 years? Like, is this just a fact of life? So usually it's because you want to change things, because you realize there's some other way to do things, or a better way to do things, or a way that didn't exist before. But some changes are really hard or almost impossible to make without breaking binary compatibility. So in the 2.11 to 2.12 transition, the biggest of these changes, there were multiple ones, but the biggest one was a new encoding for traits, based on the new support for default methods in Java 8, which means, among other things, that the implementation of traits was much simpler. But it also means that the encoding had to be completely different. So if you used a Scala 2.11 compiled class file, you couldn't use it with the Scala 2.12 compiled class file because they just didn't speak the same language. And from 2.12 to 2.13, the main reason for breaking binary compatibility was not at the level of the language itself, but at the level of the standard library, where the standard collection was redesigned, and in particular the hierarchy of classes, which is something that is very basically impossible to change without breaking binary compatibility due to how the JVM works. Okay, but yeah, there's always a good reason, basically. But can we maintain compatibility while still evolving Scala? And yeah, I don't really know, but maybe we should try, because breaking compatibility all the time is such it makes it really hard for people to upgrade, to try new versions. So maybe we can try to do things a little bit different and see how it goes. And I think one interesting example of how things can be done exists already in Scala, and that's Scala.js. So you can say, well, it's not really like its own language, but I mean, kind of is really. It pretends to be a compiler plugin, but it's really like a whole compiler. It does a lot of things. It's crazy. And what's really crazy is that it has maintained binary compatibility for more than 4 years, like longer than the lifetime of a Scala version. And what this means, so this means multiple things, because Scala.js provides JVM API for like using the Scala.js compiler for the SBT plugins, stuff like that. But it also, in the end, it's going to output JavaScript. But when you make a Scala.js project and you like publish your jar to Maven, the jar doesn't contain JS files. Instead, it contains SJS IR files, which is this like own custom intermediate representation that Scala.js uses. And when you compile your own project, the Scala.js linker is going to take all these SJS IR files from all your dependencies as input to eventually produce JavaScript. And that enables a bunch of interesting things like whole program optimization. Since like the Scala.js can see everything that you use, it's able to do really, really crazy optimizations. But it also means that if they decide to change how to generate JavaScript, they can still use old SJS IR files, and because there's like a version number in the SJS IR file, they can just decide, oh, this is an old file, but we know how to interpret it to make it do things the way we want to do now. And that's like the secret to maintaining compatibility for a very long time. Okay, so what do we get from that? Like, can we make our own format, which will be a bit what SJSIR is to JavaScript to JVM class files? Maybe. So the idea will be to store the output of one of the compiler phases. And based on that, we can like restart the compilation from that point on. But where do we put this thing in the compiler pipeline? So to explain that, I have to show you the compiler pipeline. So you start with some source Scala file, and then like magic happens, and in the end you get one or more class files. So now we need to get a bit deep into the magic to explain what's going on. So the first thing is we're going to parse that file into a tree. So what does that mean? So I start by parsing, let's say I'm parsing an expression like obj, here is an expression. The parser is going to see that and say, okay, that's an identifier, and the identifier is the string obj, basically. And then if I do obj.lm, then the parser, because of a dot, knows that this is some kind of selection. So that's represented with a select tree node, which takes the thing we parse for obj, and then selects lm out of it. And then if I put parents and put some constant here, then this becomes an application of something which is represented with the apply node, which as a second parameter takes a literal, which is the constant 5. Okay, so that makes sense. But once you have this tree, what can you do with it? You can't really do anything with it yet because it's only syntactic. It doesn't have any semantic information. It doesn't tell you like what the code is doing. So the next step, the big step, is typer, which is like taking this untyped tree and type checking it. And the way type checking works, I'm not going to explain like all the details because that's many more talks worth of material. But we start at the top of the root, so we have our already parsed tree. And to type check apply, first we need to type check its children. So we need to type check select, and to type check select, we need to type ident. And to type ident, we know, oh, this is an identifier for obj. So at this point, we have some information about like scopes. We know what names we already have in our current source file. We know what's on our class path. And based on that, we can say that like obj in this context resolves to a.obj, for example. And here I'm not showing the details, but basically there's another tree-like structure to represent types. But here I'm just saying like this is a.obj, but really the compiler is going to like make up some type for a, and then it's going to make up some type for selecting obj out of a. So okay, now we have the type of our leaf, and we can go back up one level to type the select. So to type the select, we need to look for some element, for some field called lm in a.obj, and it's going to get a type like maybe int to int. And once we have this information, we can then type the apply node by first typing the constant 5. And the type of 5 is 5, because we have singleton types for literals. And we know then we can just very easily see that by applying this thing to that thing, we must get an int. And there's one very big thing I've glossed over here is that typing can also create new trees. So as you're probably familiar, if I write lists of 1, 2, then this is going to be equivalent to writing list.apply of 1, 2. And the way this works is when I'm type checking list, so this is like an apply node like we've seen before, and then list is some identifier, and once I've type checked it, I'm going to look at the expected type. And the expected type is something that must be applied. And we know this because we're coming from an apply node. So because of this, the compiler is going to say, OK, I have to introduce a dot apply here to be able to type check this thing correctly. And there's many, many ways in which the type checker can create new trees. And like of course, the most important one in Scala is just implicit resolution or delegate resolution. So for excess.max, when we have seen that tree, the compiler is going to see, oh, this is actually a method that takes some given parameter, some implicit parameter, and I'm just going to give it, so it's going to resolve that parameter, it's going to create a tree for it. And the other important thing to note is that this is an idempotent process. So if we take this tree which has been typed once, and if we try to retype it again, the compiler is not going to keep inserting new trees, except if there's a bug and then it does dot apply, dot apply, dot apply. That happened before. And this is going to be very important for what I'm going to show later, but it's already very, very useful as a concept for debugging because it means that as we go through the compiler phases and we start transforming the trees, we can always like sanity check that what we're doing makes sense by redoing the type checking and verifying that indeed all of our types match are correct. Okay, so now we've seen like the biggest piece of the compiler, and now I can replace the magic by the actual rest of the compiler. So I'm going to explain what these things do. So picker is in something that exists both in Scala 2 and Scala 3, and the original motivation is separate compilation. So if you just produce some class file, in your class file you're going to have methods, and these methods are going to have types. But these types are going to be JVM types. Like if you write list of int, the JVM type is going to be list. Because because Java supports generics, there's also some extra information that the JVM doesn't use, but that Java-C uses to get type parameter information. So at some point, somewhere in that class file, we write, oh, this method that we say returns a list, actually it returns a list of int. But that mechanism doesn't support, of course, all the Scala types, because Scala has many more sort of types than Java has, and in particular, you could have higher kind types, union types, all that kind of stuff. So we need to store this information somewhere in the class file or around where we can use it, because if I compile two files, a.scala and b.scala, once I'm done compiling a.scala, and I start compiling b.scala with the result of the first compilation on my class path, I need to know the types that the Scala compiler used for the first thing I compiled. So this information is the pickling information, which is stored in the class file in Scala 2. And I'm going to explain how it's stored in .t in a few minutes. So picker itself is not going to transform any tree. It's just going to like note information and store it aside. And then it's going to take the type check tree and pass it to the next phase. And when I say next phase, it's actually next 50 phase. So all of these small phases are going to take this very high level type check tree we have, which represents our Scala program. And bit by bit, we're going to transform them into something which can be run on the JVM or on some other backend. And once we've done all the simplification steps, we get to the backend. And which the backend is just the piece of code which is going to take our trees and going to emit class files for them, or JavaScript, or some other thing. Okay, another question is, among all these things, like where should we put this new intermediate representation that we want to store? And of course, I put it in the middle. It's the pickler. Because when we are at the pickler phase, we are just after with type check trees, which means we have all the semantic information needed to understand what our program has to do. But we haven't yet done all the simplifications, which eventually allow us to run on some specific runtime. So, well, what do we put in this file exactly? What's the point? So the first main point is something that should be able to evolve as we go through new Scala versions. We have new ideas. We find things that didn't really work out. We want to be able to add stuff, remove stuff, or not really remove stuff, but deprecate stuff without breaking existing files. And it has to be as compact as possible because these files are going to be in every jar you distribute. So we try to make the format something that does not have a huge overhead. And it has to preserve all the information you need for compilation. So you need to be able to take the tasty file as input and get to the same thing that you would have gotten if you had started from the source files. And then, as long as we're doing all of that, maybe we can add some extra information that can be used for tooling, like IDs, REPLs, documentation generation, etc. Okay, so now I'm going to explain the binary format of tasty in some details. And to make that less boring, I'm going to use like nice diagrams. So the first thing is this awesome constant, which is how you see that a file is a tasty file. And after that, the next two things are represented as natural numbers, and I'm not going to show which encoding we use for natural numbers. And they represent the major version and the minor version of the format. And like the end goal is this thing is going to be fixed for like the next century, and we can just increment the minor version without breaking compatibility. After that comes the name table, which is where we store all the names that we're going to refer to in our program. And after that comes a bunch of sections, which are where we actually put the type checked abstract syntax trees. By the way, that's why it's called tasty. And any extra information we want. So there can be one or more of the sections, which is why you have this loop here. So the name table is just, you need to, when you encode it, you have to choose, like, you have to write down its length, and then you just write down a bunch of names. And names are interesting. Names are not just like a bunch of string constants, but they can have some semantic information. So you have just basic names, which are just like a bunch of UTF-8 code points. Then you have some more interesting things like qualified names. So for example, sometimes we need to represent scala.int, and we could represent it as a string, where the dot is how we see that this is actually qualified things. But this is pretty problematic because it becomes very hard to distinguish between the names that have a meaning that the compiler uses and the name that the user wrote down, especially in Scala, where you can put pretty much anything you want in the names of the definition if you just enclose them in backticks. So a qualified name is represented using some tags, so this is some constant, then some length information, and then there's two subparts of the qualifier, so in this case it will be Scala, and the thing you're selecting, which in this case will be int. And nameref is just going to be a natural number, which is going to be an offset in the name table. So these are just pointers to other things. Okay, now we get to the meat of the tasty format, the tasty meat, which is the abstract syntax tree section. So it starts with a string, which isn't really a string. It's going to be an index in the name table, but you get it. And then a bunch of statements. And a statement, I'm not going to show all of them because there's a bunch of them, but those are basically the trees of the format. So you can have a package tree to represent a package, an import tree, a tree for defining a val, And those are very close to how they are represented internally by the compiler. So for example, a val is something which has a name, it has a type, it may or may not have a right-hand side because it might be abstract, and it can have modifier like private, that kind of thing. And then the other important part is types themselves. So types, there's also a lot of them, as you might have guessed. But a few interesting ones that you might recognize is type bounds. So this is like when you write super type of something, subtype of something, we represent that with a type bounds tag, followed by the representation of the lower bound, followed by the representation of the higher bound. And the type application, like list of int, that's represented with an applied type tag, the representation of lists, and then the representation of its arguments, which can be 0 or more. And then terms. So that's very close to what we've seen before with the ident and select nodes. But here we are at the level of the tasty format, so it's a bit lower level. And here there's an interesting, an important point that's not very obvious, is that not all of the terms have types, but we're in a typed language, so what does that mean? So in fact, to avoid wasting space, we don't need to store the types of everything, because we only need to really to store the types of leaves of the tree. So for example, the identifiers, once we've looked up in the scopes what do they represent, we can store that information in the type of the ident tag. But when I do an application, I don't need to store the result of the type of the application, because when I'm going to read the tasty tree, I can just look at the type of the function, the type of its arguments, and then I can find again the type of the application. And now we get to the extra sections, which are after the abstract syntax tree section. So very simple one, but very useful one is just the comment section, which is going to store every Scala doc comment in your file. And the way this works is for every comment, we're going to store the pointer to which definition in the tasty file it refers to, the length of the comment, the set of code points which represent the string of the comments, and then the position of this comment in the source file. And this information is completely useless for compiling, of course, but it's really useful if you're an IDE and you want to show to the user a comment, the documentation comment for the thing he's hovering over. And we are also using it, for example, in the .t REPL, where you can type :doc space and then the name of some method, and it's going to look up the documentation comment from the tasty file. And that's a much more direct way than going through, like getting the source jar, parsing it, and trying to match that with the trees you have in your compiler. And finally, a very important section is the position section, which stores the position, so the offset from the beginning of the file of every tree that has been written by the user. I say user written tree because, as we've seen before, when you type check your program, you're going to create new trees which are not written by the users. And so these trees, you need to be able to distinguish them from those that the user wrote, because when you hover over something in your IDE, for example, you want to see the type of the thing that's written down and not the type of the synthetic thing the compiler put on top of your code. And this uses pretty interesting delta encoding that I'm not going to detail because it's a bit complicated. But you can see the full grammar with an explanation of this in the tastyformat.scala file in the .t repository. Okay, cool, but like, what can we do with that stuff? So very concretely, we can start with a problem. I have a library A, which is compiled with Scala 3.1. I want to use it with Scala 3.2. How do I do that? Do I wait for the authors of library A to republish it for Scala 3.2? I can do that. Otherwise, if I'm very impatient, I could fetch the jar for A, delete the class files because they don't matter, and just regenerate them from the tasty files which are also in the jar. And instead of doing that by hand, you could imagine that your build tool can automatically do that in the same way that when you're working with a build tool that works on sources, it's going to automatically fetch the sources and compile them and cache them for you. Your build tool could fetch the tasty and compile them and cache them for you. And that's an idea I hadn't thought about that Jason Zog proposed a few days ago. You could imagine that you have something like Maven or a mirror of Maven that can automatically, from the existing jars published to Maven, create new jars with updated class files, which I think would be pretty cool, because it means that this will work with any build tool you want, even Ant. Of course, this isn't really a silver bullet. This is only going to work if the standard library of 3.2 is designed to be compatible with the standard library of 3.1. The kind of things that this can help with is if, for example, in Scala 3.2, we change again the encoding of traits for some weird reason, or if we change any of the details of how we encode things after type checking and before code generation. So you could say, okay, well, I could do that, or I could use the source files and compile everything from sources. And that's pretty much the same then. But it's not really the same because when you're using source files, you don't have binary compatibility as a problem, but you have source compatibility. And in particular, when you upgrade Scala version, because the type checker evolves and because type inference is so powerful in Scala, it's possible sometimes that your program stops type checking or does something slightly different just because type inference now works in a different way. You don't have this problem when you use tasty, because the tasty trees are after type checking, which means we have resolved the implicits, we have inferred all the types, we have resolved the overloads. So all these kind of things which can change depending on what the compiler decides to do with the code you wrote are not going to change. So tasty, of course, if it was just this binary format, you couldn't really do anything useful with it. But we have some tooling around it, which makes it much more useful. So first, we can, of course, generate tasty files, and that's super easy. You just take .t, you compile stuff, and next to your .class files, it's going to make .tasty files. And then you can also compile from .tasty files directly using -from-tasty when you run the compiler. You can also decompile, and decompiling basically means taking the tasty trees and then printing it. And that can be done using the -decompile flag or just by opening a .tasty files in VS Code when you have the .t plugin installed. Okay, and so far, tasty is basically the internal format used by .t, but we have bigger aims than that. We want it to be the format for intermediate representation of all of Scala. And to prove that this can be done, there's a proof of concept Scala 2 plugin we wrote last year that can take a Scala 2 trees and convert them into tasty. And so far, this has just been a proof of concept, but we'd like to try to get this into a more usable state. And the main remaining technical issue to fix to do that is just to move all the logic around tasty, which is currently part of .t itself, into its own project, which will cross-compile between Scala 2 and Scala 3. And once we have that, we can also think about doing the other direction where we take .tasty files and produce, and Scala 2 is able to understand them. And if you can do that, that means you could use .t libraries in Scala 2 projects. Of course, there's a big asterisk here. There's many things that need to be taken into account to make sure that this is possible. But in principle, this is something we can achieve, I think. Okay, and now that you've seen all that, you might wonder, okay, well, should I use this tasty thing to build tools? And the answer is most of the time you don't actually need to, because there's this different but very much related thing called tasty reflect. which is going to be easier to use because directly manipulating tasty trees is not easy. Whereas tasty reflect is something that whose main use case is replacing Scala 2 macros and provides an API which is similar to Scala 2 macros where you're manipulating trees using a library. But it can also be used for tooling because the trees that tasty reflect exposes, whereas in Scala 2, the macro API exposes basically the compiler internals. Tasty reflect tries to expose something which matches the tasty spec, which means it should be something that can be evolved and something which you can rely on for tooling. And in particular, we wrote .tasty to .semanticdb transpiler, basically, which works which is implemented using tasty reflect instead of like as a compiler phase or something which directly reads tasty trees. And we also have a work in progress implementation of which takes .tasty files and generates HTML documentation, so a Scala doc replacement basically. And that's very interesting because if you start from .tasty to generate your documentation instead of starting from sources, then that makes documentation generation much faster because you don't have to type check your root program just to be able to generate HTML. And for more information, you should go see Nicolas' talk on metaprogramming tomorrow. Thank you very much.
People have questions?
So it sounds like you could take the tasty files and pack them into the jars to put up on a repo?
Yes.
Is that what I'm understanding?
So when you, by default, when you compile stuff with the compiler, you're going to get both the class and tasty files in the same output directory, and they're going to be part of the jar that gets published.
Okay, so the second follow-on is if you can make a pretty print image of what went into the compiled code, doesn't that mean that you need to do obfuscation or something to keep people's code
Yes.
secret?
So if you, well, so when you have Java bytecode, you're already like very close to source, and you might want to obfuscate that if you really don't want to share your code. And in the same way that with Tasty, you could obfuscate it, but that's pretty complicated. Instead, what you could do is just, and what we probably will offer is a way to not generate the full Tasty trees with all the implementations, but just generate enough information to get the types of all the methods in your program, which is the bare minimum needed to do separate compilation. And that's not enough to do things like inlining, where to inline a method, you need to actually get the code of that method, for example. But for a lot of other use cases, you don't need the full information of Tasty, and we could have a mode where the compiler doesn't generate this information.
Hello, can you hear me? What about the JDK? I mean, Scala also makes use of a lot of Java libraries, right? So, do you also store which version of the
Which
JDK?
version of the JDK? So no. So it's true that if you write your own library that uses a specific version, like if the Scala standard library suddenly is compiled with Java 12, you won't be able to use it in your project with Java 8 easily. If it uses new methods which have been introduced since Java 8, there might be a good point that we should have a field in the Tasty which references which version of the JDK we are compiling against. But in general, this is the same issue you'd have with any dependency. Like if you use some specific version of a dependency, then everything that depends on you need to use at least this version.
Yes, if I'm starting a tooling project right now, should I focus on Tasty or Semantic DB, or in which use cases should I choose one over the other?
It depends on what kind of tooling you're interested in. So the binary formats themselves are probably not what you want to focus on. You want to focus on what gives me the APIs to do the things I want to do. So like Scala Meta uses semantic DB as a way to store information. But the interesting part is more like the APIs that Scala Meta gives you to do cool stuff. And if these APIs are what works the best for your project, then you should use that. If you're more interested in doing something that can use new features of Scala 3, for example, then maybe you can try using Tasty Reflect instead. So it depends, basically.
In your one example, you explained that you will still have this standard library compatibility issue, like when you said, okay, I'm going to use something in 3.2.
Yeah.
How is this going to be solved, or like, is it solvable, and what are your plans to do that?
Yeah, so the issue will be if suddenly Scala 3.2 decides to change the name of list to something else because they didn't like the name, like that will be very hard to make compatible. It's not impossible to imagine some way to paper over that kind of things, but I think what we'd like to do instead is just have more discipline, saying, okay, now that we have tooling, the ways that maintaining binary compatibilities for like many years is a possibility. We just need to be more strict in how we evolve the Scala standard library. So like not redesign it every 2 years, which I think people will also appreciate.
Other questions? Yeah.
In a kind of related question, like, have you discussed using Java 9 modules to kind of paper over that difference by just saying, okay, well, this module depends on Scala 2.11 and this module depends on Scala 2.12, and they kind of live in the same namespace, but they use like a Java compatible API just to call between themselves, and there's no Scala types exposed between them. Like, you could kind of make that work.
You could kind of make that work, yes. But it's the hard part is you can make like isolated things using their own class loaders or whatever, but then when you need them to interact, it gets complicated. And I mean, people have been trying to do that for 20 years with like OSGI, and I don't think it's like satisfying yet.
Would it be like in the realm of possibilities to like use Tasty as a target for Java or even other languages,
yes,
so that you could automatically, use Java libraries in Scala JS or native and stuff like that?
So I think it's possible. You'd have to extend Tasty somewhat, maybe for some of the features of the languages that couldn't be expressed in Scala, but I think it's a very interesting thing to explore, because it's true that if you can, even if you are like a language writer, you make your own language, if you can use Tasty as a backend, then you get a lot of things for free. You get super optimized JS backend, JVM, native eventually, and you can use libraries from the Scala ecosystem, and like tooling around Scala too. So it's I think it's a very interesting thing that could be explored.
So you suggested that people could or should use future Scala versions to recompile published Tasty files. Mm-hmm. And does that mean the Scala compiler will need to maintain backward compatibility for the semantics of what a Tasty tree will do in all possible future versions? And if so, does that constrain any possible
yes, so there's always this tension between like evolving things and keeping compatible. And that's why I pointed to Scala JS, which through like the lifetime of the 0.6 series has maintained compatibility for their own internal representation while still evolving it. And like, yeah, you have to work a bit harder to be able to do this. Like, you have to reinterpret old versions of files in the new way you want things to be done. But I think it can be done for the things we would like to do for Tasty.
Do I understand it correctly that binary compatibility is only on Tasty level, meaning if you have a Java library consuming your Scala library and you update your new version of Scala, that it might break?
Yeah, yeah. When I say binary compatibility, it's a bit weird because what does binary mean? Like class files are binaries, but Tasty is also binary. So to be clear, there's we will maintain Tasty compatibility, but not binary compatibility. But then even your Java project will be able to make use of recompiled class files that were compiled with a new version. But these projects themselves will not be recompiled from Tasty if they don't output Tasty, unless someone makes a Tasty backend for Java, which will be cool.
I have two questions. One is when we do cross compilation using SBT, like when we want to target to say 211.1, 212.2, those kind of things, are we going to generate different Tasty files or it's just one Tasty file? That's one question. Another is let me finish the other question. Let's say we run into this JDK compatibility issues, right? JDK class files. Would there be a way to recover? Like let's say you use the Tasty file and you try to compile with the new version of Scala 3, but it uses a different version of JDK. Is there a way to recover from it? Like only recompile or rewrite the JDK part?
It really depends. Like if like say the Scala standard library is compiled against a new JDK, but it doesn't use any of the new features of a JDK, any of the new methods, for example, then you might still be able to recompile that to Java 8 bytecode. If it does use like new methods, then like there's not much you can do, like because the method doesn't exist in the JDK version you're trying to use. And yeah, for your first question, when you cross-compile, you'd still want to emit two different Tasty files. If, say, in the new version of the compiler, you have a different way of representing things, like you need somehow to store this in a different file. And this would have to, well, you could imagine putting everything in like one big jar and using something like what Java supports, where you can put like different versions of class files in different subdirectories based on the version of Java that you're using. You can do like 8/a.class, 9/a.class in the same jar. And then one of them is going to be read by Java 8 and the other by Java 9. We could maybe have something similar for Tasty files in a jar, depending on the Scala version. Not sure how useful that will be.
Okay, one last question.
How would you work with Scala features that maybe don't exist in previous versions? So you have a Tasty file you compile with 3, and you use union types, but you want to use it in a 2.12 version.
Yeah, that's a good question. So the reading Tasty from Scala 2 has a bunch of challenges, and one of them is just that there are dirty features that don't exist in Scala 2. So you have to go on a case-by-case basis. Some of these features you can emulate. Some of them maybe will add some, like the minimum amount of logic we need in like the next version of Scala 2 to make them usable, and some of them you just, if you try to use them, they just won't work. Like the compiler will tell you, like, you can't use this method from Scala 2 because it uses a match type, and I don't know how to interpret match types. So then a library designer, when writing like the public API of their library, would have to be careful to like write things which can be interpreted by both Scala 2 and 3.
Thank you very much.
Thank you.